back to Trailer Physics with Mr. Egger. Friday, one more week down. We got about 2-3 more weeks, depending on how you count. Maybe 4 if you're fully counting. I don't know what's going on. Anyway, today, just a little bit of math day. Pretty straightforward math. Again, I'm going to go through the derivation, the equation, do 2 examples, and then you've got 3 or 4 questions on the homework for today. And that's Friday. All right, let's get after it. So all this week we've been talking about pressure. Beginning of the week, just pressure is force over area, and then the rest of the week was about how water and liquids, because atmosphere does as well, or not liquids, fluids I should say, fluids create pressure. It creates this force per area. The bigger it is, the more force there is. So how does pressure vary with depth? Well, if you've got some object, we'll call it a lake or a pool or something, it's got a depth within it, right? Some depth d. We're actually not going to use d in the equation, but more on that later. Some depth d within that fluid. The further you go down, the more pressure there is, and hopefully you've all experienced this in a swimming pool or something. When you swim down deeper and deeper, you feel more and more pressure on you, because you have more and more fluid above you. So the relationship you guys got was a linear relationship that said pressure was directly proportional to depth. Most people came up with an equation, P equals about 9.79 or about 9.8 times D, where depth is in meters and pressure is in kilopascals. Now, really this number, and then we solved a question. But this was the basic equation. Well, since pressure was in kilopascals, if we're talking about pressure in pascals, which we're going to be doing, there's 1,000 built into this. All right, so this number here is actually including 1,000 constants. More on that in just a second. But that was the results from the lab and what you saw. Last little thing, though, you saw is it didn't matter where at any given depth you measured. If you measured on the left, or if you measured on the right or in the center, you got the exact same pressure. Because pressure comes from the column of water, column of fluid above that location, above that point. Now, one more weird little thing is if I were to kind of extend off my tank on the bottom and have a little area you could swim into, kind of like a cave or something, I'd actually have a pressure down here equal to all the other pressure at that level. Even though there's no water up above that location, once you have a pressure established at any given level within a fluid, once you know the pressure at some location, that pressure is the same at all locations within that particular set of fluid. So that would all be the same pressure at that height or depth. All right, so height's the key word we're going to get to with an equation. So, equation for pressure. Well, it comes right from the thing you guys derived. Equation, P for pressure equals, now, here's where this constant comes from. 9.8. Hopefully you guys recognize 9.8 was the acceleration due to gravity. So G is definitely in this equation. But the 1,000, because it was kilopascal, was also there. That 1,000 was the density of the fluid. So the 9.8 was actually the density times gravity. Now this is a rho. It's like a P, a little P. You know, super confusing because we're doing pressure. But it's a rho. It has no little thing on it. It's a Greek letter. It stands for density. I could use capital D there. And again, height. The last thing there is the height, H, or depth. We're going to use H because this is the equation, rho GH. But depth could be that when we define the terms here. So let's do that. Each of these terms, capital P is pressure. And then this pressure, when you use these numbers or these units, we'll give it to you in pascals. Remember, pascals get some really big numbers, but let's keep the math simple. Rho is density, and that's going to be in kilograms per meter cubed. So how many kilograms per meter cubed? These are usually be in the thousands for its fluids. G is 10 newtons per kilogram, and H and this is key here, this definition, H is height of the fluid or depth, whichever one you want to think about, and it's in meters. So units will be pascals if you use kilogram meters square or cubed, and meters. So that's the equation. Now let's take a look at two examples that calculate or use this equation to calculate pressure or height or depth. So example 1 asks us to find the pressure 9 meters deep in a lake. So we're going to use our math model or equation that we now built with some of the numbers that we have for it to calculate something that I asked you in the lab. So remember, everybody in the lab, when you calculated 9 meters, you got about 87, 86 meters deep. So let's see if we get the same thing here. All right, first off, what is our, 86 or 87 kilopascals. So let's see if we get the same thing here. So what is the pressure 9 meters deep in a lake? Key here, lake is fresh water, so it's 1,000 kilograms per cubic meter. The density is going to change in some of the other problems, but that will just change one of the variables in the equation. Make sure you plug in density where it goes. For this particular one, pressure equals rho g h. So finding pressure, density is 1,000, so we'll use 1,000 kilogram per meter cube. G is always going to be 10 for us, and the height or depth is 9 meters for this. So I do it out, and I get a pascals. 1,000 times 10, I get 90,000 pascals. You guys got 86. What's the difference? Actually, the same number. You guys got 86, 87 kilopascals in the lab yesterday. This is 90 kilopascals. Kilo means 1,000, so this is 90 kilopascals. Sure enough, you get the answer that you guys got by using the math equator. All right, so then we can also solve for other things. What if I know the pressure? How deep do you need to be to get that pressure? So in this particular example, just how deep would you need to be in that same lake to have a pressure of 1 million pascals? All right, so it's the exact same equation. P is rho g h. In this case, I know pressure, 1 million, 1, 1, 2, 3, 1, 2, 3. Density is still 1,000 kilogram meters cubed. Gravity on Earth didn't change. And I'm solving for H, or depth. If I take 1 million, divide it by 1,000, then divide it by 10, or multiply that, whatever I do, solving for H algebraically, I get an H, or depth, of 100 meters. So 100 meters deep will give me a pressure of 1 million. All right, you guys go try the 4 questions on the homework. It's just one page. I tried to get it all on one page. This is the key equation. Pressure equals rho GH. Just solving for different things. Make sure you identify the right variables. Again, I may change the density on you, so make sure you use the right value for the density for each of the questions. Have a good one, guys.